on this section, we'll look at electrophilic aromatic substitution reaction. And before me presenting, there's a question. This question reads, okay, using a plain benzene ring as your starting material. So we're using benzene ring as our starting material in this reaction. Show the reactants, okay, the catalyst, the product, the mechanism, the energy diagrams, the order of synthesis to produce this drug. So we're asked to synthesize this drug here, and these are the points we have to follow in synthesizing this drug. So they asked us to show the reactants, the catalyst, the product, the mechanism, the energy diagrams, and the order of synthesis. So let's pay particular attention to this question. It weighs more than 20 marks. That means each and every step is significant in attaining those 20 marks. So let's watch the video till the end. Alright, so to begin this off, we'll start with the step we call analysis, where we deduce the order of the synthesis. So in this step of analysis, we'll have a plain benzene ring, and we'll analyze based on the nature of these attachments which reaction will be reaction number 1 and which reaction will be reaction number 2. Okay, so without further ado, let's begin the synthesis, and let's write down these points to give us our idea of the product that we're going to form. So kindly take note of these points because I'm going to erase them for the following reaction. Alright, so this will be the order that we will follow. Okay, so in synthesizing this reaction, ladies and gentlemen, we consider the groups. Number 1, we consider the groups attached to this molecule. So this molecule had an acyl attachment. So we had an acyl attachment at this carbon right here. So what we see is this acyl attachment is at this carbon right here. So if we have an acyl attachment, we also had a bromine attachment at this carbon right here. So let's look at the nature of this group and the nature of this group. Alright, so this acyl group is relatively electron withdrawing. Okay, so this is an electron withdrawing group. Okay, because the atom that is directly attached to this benzene carbon is as well directly attached to a more electronegative atom, and the more electronegative atom is pulling the electrons closer to itself. So we realize that the carbon here will have a relatively partial positive charge. So that partial positive charge will allow for it to have a deactivating effect towards the ring. So that means it's going to make the ring less nucleophilic by pulling electrons away from the ring and towards itself. So this is an electron withdrawing group, and it is a deactivator. So this also deactivates the ring by making it less nucleophilic. And not only that, this electron withdrawing group is also meta-directing. Okay, this is a meta-director. So we discovered to say, once we have this molecule on this carbon here, the only position of the incoming molecule will be this meta position. Okay, so this is a meta-director. So let's take that note of that. And then let's look at our second atom, which is attached, which is the bromine atom. So the bromine atom is relatively electron withdrawing as well. It's an electron withdrawing group, although it is a weak electron withdrawing group. Okay, so this electron withdrawing group has properties, and one of the properties is that it is a deactivator. We know that all the electron withdrawing groups are deactivators. It is going to deactivate this ring, but it has a peculiar property, and all halogens possess this peculiar property, which is it is ortho-para directing. So despite it being an electron withdrawing group, a deactivator, it is also ortho-para directing. So halogens are the only compounds that are deactivators, and they are ortho-para directing. Alright, so that means that this bromine can allow for the incoming group to sit on the ortho position, which is this position right here, and the para position, which is this position right here. So let's have those points in check, as they will be the guiding principles in the analysis step. Okay, so let's look at the analysis step. So in this step, I'll erase these groups. Okay, and we have our plain benzene ring as the question requested. So this is our starting material, and we want to see the order of the synthesis. So how we deduce the order of the synthesis is through analysis. We have to analyze each single group on the ring and want to see the effect that group will have on the incoming molecule. Alright, so in the first case we'll use the bromine. Okay, so the bromine is a deactivator. Although it is orthopara directing, it is the only deactivator which possesses this property, as also the other halogens. So all halogens possess the property of being orthopara directing deactivators. Alright, so in this first step of this work, we see that when bromine is attached to this benzene ring, the incoming molecule, which is the acyl group, so this acyl group, which is the incoming molecule here, is going to attach itself on the ortho and the para positions because of the effect of this bromine. So if we attach bromine first, we expect the incoming molecule to only sit on the ortho position, which are these two, okay, and the para position, which is this one. Okay, so from this information, let's look at our synthesized molecule. So this analysis is critical analysis. I like to do this analysis before any reaction. It's a very helpful step. It will give us a clear vision on what happens next. Right, so after we add this group of bromine, we realize to say the incoming molecule, which is the acyl group, can sit on the ortho position and the para position. So in the original molecule that we had, the drug, this was the setup where we had the acyl group at this position and the bromine at this position. So if the bromine was the first molecule, we see to say we are able to realize this drug because this acyl group is on the para position and it's able to bring in an incoming molecule at the para position because it's also para directing. So starting with bromine passes, that is the analysis step. So we try out a single unsubstituted benzene ring and we see the effect that one group has on the incoming molecule, and we see if it coincides with the drug we are to produce. Right, so we've analyzed the substituent group number 1, and we have seen that bromine is able to be the first molecule. If we are able to do a series of reactions, we can start with bromine. And let's just confirm this by trying out if perhaps starting with the acyl group can yield the same results. So we'll do second analysis, and in the second analysis we use the acyl group instead of the bromine group. Okay, so we'll draw our plain benzene ring as well. So this will be our plain benzene ring right there. Okay, so if at all we started with the acyl group in the first reaction, we would expect the acyl group to be here. Okay, this is our acyl group right here, and we know that this acyl group is electron withdrawing. That means it's going to have an orthopara direct meta directing effect. Sorry, so all electron withdrawing groups possess a meta directing effect. So they are meta directors. So all electron withdrawing groups are meta directors, apart from halogens. As we've seen in the previous case, the halogens were directing in the orthopara position. But as compared to these halogens, these acyl groups and the other electron withdrawing groups are different because they are all meta directors. So all electron withdrawing groups are meta directors. So if we are to begin with this acyl group as our first molecule, we discover to say the only possible positions of the incoming molecule are going to be the meta positions. So we deduce to say only this position and this position can be occupied by the incoming group. Okay, so if only this position and this position can be occupied by the incoming group, let's see if it coincides with our drug that we have been asked to synthesize. So this is the drug that we've been asked to synthesize. Right, that is the drug molecule we are to synthesize. So based on the meta-directing effect of this acyl group, we've deduced to say the only possible positions for this bromine to be attached are the meta positions, and this does not coincide with the drug we have. The drug we have has an attachment on the para position, so that cancels out this acyl group. So in analysis, we've deduced to say the first molecule we use will be the bromine. We'll halogenate the ring first because the bromine is orthopara directing and is coinciding with our drug. Right. So based on this analysis, I'll draw the following conclusions. Okay. So for the order of synthesis, yes, so the order of synthesis will be the first reaction. So reaction number one. Reaction number one will be a halogenation, where we use bromine. Okay, so this will be reaction number one based on the analysis, and reaction number two will thereby be acylation. So that will be acylation of the benzene ring. So with this order of reaction established, we can therefore now arrange these into the series of reactions that will be followed through, beginning with halogenation. So halogenation will be the first reaction. So we'll look at the complete reaction of halogenation, and we'll look at the complete reaction of acylation. Okay, so let me start with halogenation. So when we're halogenating, let's not forget the raw materials we've been given. We've been given raw materials to be benzene. We've been given our raw material to be benzene. So now we have to halogenate this benzene, and we know that the reactants we use are bromine itself, Br2, and iron bromide, okay, Br2 as well. So this is our catalyst, our Lewis acid. This is our reactant, which is the bromine, and this is our raw material, which is benzene. So from this reaction, we are expected to yield this product. Okay. Accompanied with that, we produce back the iron bromide, our catalyst, and we also produce hydrogen bromide. Yes. So these are going to be the products of this reaction. So this will be reaction number one. So this being reaction number one, we understand the mechanism of halogenation. If you don't understand, please let us revisit the previous works on halogenation, and let's revisit the mechanism of halogenation. For that will be cardinal, and we will need to apply it here. So this is the overall reaction number one. Okay, so the key point to take is that in reaction number one, the product of reaction number one becomes the reactant of reaction number two. Right, so let's take note of this major product here. It will be very cardinal in reaction number two. Right, so our analysis is able to guide our reaction from catalyst to product and more product based on how we've arranged these atoms. We are able to realize the drug that we've been required to produce. Okay, so this is the first reaction. So I'll write the reactions in singles, and then I'll write it as a complete reaction consisting of the two reactions, which is halogenation and acylation. So for reaction number one, this is the reactant. So let's indicate reactant. So we indicate R for reactant. So this is reactant. Then this is our catalyst. So we indicate a C. And then this is our other reactant. we indicate another R. This is our product, we indicate a P. This is our catalyst, we indicate a C. This is our other product, we indicate a P. Right, so these are the reactants, products, and catalysts of the first reaction. So without further ado, let's look at the second reaction, which is acylation, where we use this product as our reactant. Okay, so reaction number 2. So reaction number 2. So for reaction number 2, reaction number 2 will be acylation, where we have to acylate this product, that product of reaction 1. And this product of reaction 1 was our bromobenzene. Okay, that is our bromobenzene. So let's acylate this bromobenzene. So as we can notice, this is orthoparadirecting. Bromine is a halogen, and all halogens are orthoparadirectors. So we are seeing this position and this position to be the most, actually the ortho position, which is these ones here. Let's take note. Ortho position here, and the para position to be the possible places for the incoming molecule. So let's write our reactants for the acylation process. So acyl group always has a carbon double bond to oxygen and a CH3 attachment, and we have a halide. So the reactant for the acylation process is an acyl halide. So an acyl halide is used. So in this case, I'll use acyl chloride. So I'll use acyl chloride as my acyl halide. Okay, so acyl chloride there, and then as the catalyst we have iron tetrachloride. So iron tetrachloride is our catalyst for this reaction. So what do we expect to produce? So seeing to it that this is orthopara directing, and looking at our drug, the position of the acyl group was in the para position. So that means we'll attack on the para position, and our product will produce an acyl group, will have an acyl attachment on the para position. So after this reaction occurs, we'll produce this molecule here. So the bromine. So this will be our product number 1. So we have a product on the para position. So we have an acyl group here. Okay. Alright, so this is actually perhaps the drug that we're asked to synthesize. So we've actually synthesized this drug following the correct order of this synthesis. And this isn't the only product to be produced. We can also produce an alternative product which has this acyl group. Okay. Which has that acyl group in the ortho position. So we have another product in this form, because the bromine itself is orthopara directing, so there will be some percentage of ortho product formed and some percentage of para product formed. But in this synthesis, we are more particular to this product, the para product, because it's the one coinciding with our drug molecule. Alright, so apart from this product, we also have our catalyst realized. So we still have iron tetrachloride, and since we used chlorine there, we've produced hydrochloric acid as our byproduct. Okay, so this is now the overall reaction of the acylation of bromobenzene, which is the second reaction of this synthesis. Alright, so with these points in check, we'll understand the order of synthesis of this reaction, and let us not forget to label each reactant with an R, catalyst with a C, reactant with an R, product with a P, and another product with a P, catalyst with a C. Okay, like that we have indicated. So with this information, the only thing we have to show below is the mechanism. So we have to show the mechanism of this reaction, and perhaps we have to include the energy diagrams. So let me show the full order of this synthesis from the first reaction to the second reaction, so that we deduce energy diagrams and we see the order